Now let's prove a really important property of trees that's going to help us as we prove even more important properties of trees soon. Um, every tree has a leaf. Okay, so the theorem is, hey, let G be a tree, then there exists at least one node in G with the property that that node has degree 1, and those degree 1 nodes are what we call leaves. So this proof is mostly a proof by picture, but I'm also going to show you the written out version here. Here's the idea. We're going to start with a tree, and we're going to let U and V be the two nodes with the longest path between them. So here's a graph. This graph is indeed a tree. Um, and I'm going to look for the two nodes that are farthest apart in terms of path length in this tree. So I'm going to choose node V, which is all the way over here, and then node U. These are 3 edges apart, 1, 2, 3. I could also have chosen this node for my U, but I'm allowed to break ties arbitrarily. That's fine. So this path, U to here, and then to V, is a path of length 3 that is at least tied for the longest path in my tree. Okay, so what I'm going to do is I'm going to prove that node V over here is a leaf. We're going to do this by contradiction. So let's assume to contradiction that V is not a leaf. Okay, so if you're not a leaf, that means your degree is not equal to 1. Your degree can't be equal to 0 because then you'd be an isolated node hanging out here and the graph would not be connected. So instead, it must be the case that the degree of V is greater than or equal to 2. Now, that can only happen if there is some additional edge out here with an additional neighbor that I'll call W. Okay, so what's the deal with W here? First of all, we know that W, our guy W over here, cannot be connected to any other nodes on the path from V to U or back. So for example, if it were the case that W was connected up here, we would have created a cycle. This guy, that cycle, not allowed. So it must be the case that W is not connected to any of the nodes on that path. Okay, but now if we know that, then hey, wait a second. I have a problem. The only way for me to get from U to W is to go 1, 2, 3, 4 steps. Path of length 4. My problem here is that I assumed that my path from U to V was the longest path in the graph. Indeed, that's how I picked U and V. So I had this assumption that, hey, this path is the longest path in the graph, U to V, three steps. But now there is a pair of nodes, U and W, that have a path of length 4. That's a contradiction. That contradicts how I picked U and V. Since I know that there has to be a pair somewhere in the graph that has the longest length, and I just showed that that's only possible if the degree of one of them is equal to 1, I've proven, hey, the degree of V in this case must be equal to 1. This edge is not possible. So, in summary, I've shown, using proof by contradiction, that every tree must have a leaf, a node of degree at least 1. And indeed, we found a recipe for finding them, actually. Choose the longest path between 2 pairs of nodes, and the endpoints will be leaves. There is one more big property of trees that we are going to prove, and that is the number of edges in a tree. So, theorem, let G be a tree with n nodes, then it's the case that G has exactly n minus 1 edges. So if we kind of imagine testing this out, here's a tree that I'm going to draw with 3 nodes. Guess what? This tree has 3 minus 1 equals 2 edges, so we've illustrated the theorem. So how do we prove this? We're actually going to use induction, and we are going to use the previous result about every tree having a leaf as well. So here's the beginning of our proof. We'll work by induction. So our base case, n equals 1, we're thinking about a tree with n equals 1 nodes. Hey, look, if you have one node, so here I'm going to just draw a tree with one node. No edges. Okay, well that checks out because a tree with one node, according to the theorem, has 1 minus 1 equals 0 edges, and that proves our base case. For the inductive step, I want to go ahead and show the whole inductive step and also draw a picture that's going to let us illustrate the inductive step. So a lot of text here. Assume that any tree with k nodes has exactly k minus 1 edges. This is going to be our inductive hypothesis. Assume that any tree with k nodes has exactly k minus 1 edges. So following our standard induction structure, now we want to show that this statement is also true if we replace k with k plus 1 and k minus 1 with k. So I want to use this assumption to show that any tree with k plus 1 nodes has exactly k edges. So with that in mind, let G be a tree with k plus 1 nodes. We want to prove that G has k edges. What I'm going to do is I'm going to choose a leaf of G. I'm going to choose, how about this leaf right here? I'm going to choose this leaf. So I know it's guaranteed that I'm able to choose such a leaf. There is such a leaf for me because by the previous theorem we proved, every tree has a leaf. So I'm just saying, hey, let's grab that leaf. Okay, so once I have U, a leaf of G, then what I'm going to do is I'm going to look at V, the neighbor of U. Okay, so every leaf is a node with degree 1. It has exactly one neighbor. So here it is. Let's call it V. And what I'm going to do is I'm just going to delete the edge connecting U and V as well as U itself. So I'm going to see if I can draw this nicely. So here we are. Okay, so I'm going to try to not totally remove it from visualization. But yeah, so there we go. So I'm going to imagine deleting that edge. And now let me ask myself, what is left? Okay, so I don't have U anymore, and I don't have the edge anymore. What's left in my graph? Hey, guess what? It's a tree. How do I know it's a tree? It's because I deleted a node U that's a leaf. Deleting a leaf doesn't destroy any paths between other pairs of nodes. It doesn't disconnect the graph, and it definitely didn't add any paths. So my result is still a tree. So I'm going to call this G prime. But guess what? This G prime has fewer nodes. I started with G, a tree with k plus 1 nodes. Then I deleted one node, and now I have a tree with k nodes. Okay, so by the inductive hypothesis, the tree G prime that's left has k minus 1 edges. Okay, so if I deleted one edge and the result was k minus 1 edges, I must have started with exactly k edges. So the original graph G, the graph where I undelete the deleted edge, that graph must have had exactly k edges, and that's what I wanted to prove in order to complete my inductive step. So I'm done. Every tree on n nodes has exactly n minus 1 edges, no more and no less.